Everybody, welcome back. This is chapter 9, and this time we're talking about electron configurations and how we can use the periodic table to help us write electron configurations. So the goals of the section are to relate the electron configurations of the elements to the shape of the table, and then to determine the expected electron configuration of an element based by where it's located on the periodic table. So the shape of the periodic table mimics the filling of the subshells with electrons. So each row, which we call a period on the periodic table, represents the highest principal quantum number shell for the elements in that row. So all of the elements in row 3 of the periodic table, the one that starts with sodium, the highest principal quantum number for that row is 3. That's the row number. So they're going to have electrons in like 3s and 3p orbitals. All of the elements in that row have the same highest principal quantum number. So sodium's highest principal quantum number is 3. But so is magnesium's, irons, zincs, and chlorine all the way across that row. And then when you move left to right across the subshell, across a row, filling up electrons, the periodic table is arranged that the different areas of the table exactly line up with where the S, the P, the D, and the F subshells are located. So we were previously using these filling diagrams, right? The ones that like you start at the top and then you go down and then you come back around and then you do the next one and you go back around. And you can still use that. Those always work. But if you learn how to use the periodic table filling method, then you don't need to use this. You can just look at the periodic table and know how to fill up those electron configurations simply based on the shape of the periodic table. Okay, so here we go. So the periodic table is laid out so that the subshells, the different shaped orbitals, are located in specific regions of the table. And we call these blocks. So we have here what's called the S block, which is where, as you're filling electrons, remember periodic table reads left to right. So you start right here and it reads across and then you go down a column and left to right. So as you're filling, you always start with your first electron here at the start in the S block. And you fill across and then you go jump down and then you're in the next S block and then you fill across in the P block, and so forth. So remember, it always starts at the top. It reads left to right, top to bottom. So it's arranged so that the different subshell shapes are specifically in regions of the periodic table. So the S block is where the S orbitals are located. And it's organized by row number. So the first row, this would be the 1s block. And over here, you skip over, you're still in the 1s block. And that's because 2 electrons can go in the 1s block. So the first electron is added in this box and the second electron's here. Then you go down a row. Now you're in the second row. So now this is 2s, 1, 2s, 2. And then as you're filling, keep going across, you hit the P block. Now this would be 2p, because we're in the second row, and the first electron, and then 2p in the second electron, 2p in the third electron, all the way to 2p and that last electron, 2p6. So if you needed to write the electron configuration, say for neon, neon is right here, Ne, you could do it by following the periodic table. So the first orbital will be starting again, always start up here, would be 1s, the first row number, and you're starting the S block, so 1s. And neon has 10 electrons, so we need to add till we get to 10. So 1s2, that's this and this. Then you drop down, and now we're in the 2s block, so 2s, and we need to fill it all the way up because we need to add 10 electrons to get to neon. Then we move across. Now we're in the 2p block, and we need to fill that all the way up with 6 electrons. And that's the electron configuration for neon. So you can use the periodic table to help you fill these up instead of using that kind of zigzagging diagram. Let's do some more. So we've got our S block, 1s, 1s, then you drop down to 2s, 2s, 2p, all the way to 2p6. Then you drop down to 3s, 3s, These are all ones, 3s1. Second electron, and then you skip across, and now you're in 3p, 3p1, 3p2, etc., all the way to 3p6. Now you drop down, you're back to the s block, so this would be 4s. It holds one electron. 4s, you add that second electron, and now we get to the transition metals. So the transition metals shown here, these are part of the D block. And when we number the D block, the number is n-1, which means it's the row number -1. So 1, 2, 3, 4, 6, 7. So our principal quantum number, the highest quantum number that the electrons will have, is related to the row number. So highest n is the row number. So for example, if you have a hydrogen atom, its electron configuration is 1s2. Its highest principal quantum number is 1. If you have, say, silicon right here, it's in the third row, so its highest principal quantum number is 3. When you get to the D block, the D block's principal quantum number is n-1. So we were in the n of 4 period. So this would actually be a 3D block. So 3D1, 3D2, 3D3, all the way up to here. And remember the D block, the D orbital subshells can hold up to 10 electrons. So this would be 3D10, and now that one's filled. And then you go back to a P block. P blocks get the same number as the row number. So this would be 4P1, 4P2, all the way across to 4P6. Then you drop down, you do it again. Now we're in the 5th row. So the S and the P orbitals get the same number as the row number. So this would be 5s1, 5s2. The D block, it's -1. So this would be 4d1, 4d2, and it goes all the way across to 4d10. Now you're back to the P, so it's 5 because you're in the 5th row. P1 all the way to 5P6. Let's go down one more because now we're going to start hitting the F block. So we have 6s1, 6s2. And then remember, with the way the periodic table is set up, the F block is supposed to be, the lanthanides and actinides are supposed to be right there in the table, but we don't put them there because it makes the table too long. We drop them down and have the lanthanides and actinides down here. So as you're filling, you need to remember that. So when you fill across here, like let's say we wanted to write the configuration for whatever this element is here, cerium, you fill across, 6s1, 6s2, and then you have to drop down here, and we're in the F block. And the F block, it's numbered as n-2. So in the F block, we'd have, we're in an n of 6. This would be 4f1, 4f2, 4f3, all the way across. And remember, an F subshell holds 14 electrons. So this would be 4f14, and then it's filled up. And then you continue along into the D block. The next one down, we kept going down a row. We get to 7s1, 7s2. Then you hit where the lanthanides and actinides should be. So you got to drop down. And this is an n of 7. So we have to subtract 2 to get the F number. So it's 5f1, 5f2, all the way across to, oops. 5f14, because an F subshell fills up with 14 electrons, and then you would continue here in the D, 6d1, 6d2, all the way across. Let's put that in white so it matches the rest. All the way across. 2, 6D, 10. This is 5D. So when you use the periodic table to fill electron orbitals, you don't have to have that little tree memorized. You can use the shape of the periodic table and counting boxes essentially to fill up all your electrons. The important things to remember is you want to number down. Each row number is the highest principal quantum number for elements in that row. And the S and the P blocks are always equal to the row number. S and P, the number equals the row number. So when you're in the third row, you're going to be filling 3 s orbitals and 3 p orbitals. When you're in the 6th row, you're going to be filling 6 s orbitals and 6 p orbitals. But for the D and the F, we have to adjust. So for the D block, it's the row number or the n number minus 1. And for the F block, the F or block subshells are going to be labeled as the n number minus 2 or the row number minus 2. So let's jump in and get some practice using the layout of the periodic table and these orbital blocks to fill electron orbital diagrams. So I have a slightly different looking version of the periodic table here because it shows the coloring of the blocks, but it also gives us our element symbols so we can look up what these elements are. Okay, so let's use the layout of the periodic table to write the electron configuration for phosphorus. So you want to figure out where phosphorus is. It's right there, and how many electrons it's going to need. So phosphorus has 15 protons. So if it's neutral phosphorus, which we're going to assume because it doesn't say anything else, it's going to have 15 electrons. So we're going to fill following the periodic table until we've added 15 electrons. So remember, you always start up here. So our first orbital is going to be 1s. So that's this box, and then we go across, and then we're still in the s block with helium. But now we've added 2 electrons, 2 boxes, 1, 2, 2 electrons. And then we go down a row because the periodic table reads left to right, top to bottom. So left to right, we get to the end, then we come back around. And now we're in the 2s block, 2s. And we're going to add 2 electrons there. So that's that box and that box, 1, 2. And you go across. Now we're in the 2p block, so 2p. And we've got to fill that all the way up because we've got to get to 15. So we're going to add 1, 2, 3, 4, 5, 6 electrons to that one. And then we drop down to the next row. We're in row 3, so this is 3s. We're going to fill that. 1, 2, go across, and now we're in the 3p block. And we need to add 1, 2, 3 electrons there to get to phosphorus, our target. This is phosphorus, so we had to add 1, 2, 3 electrons to the 3p block. Now we have the electron configuration for phosphorus. Using the shape of the periodic table to get there and just counting like the electron boxes, like each atom represents adding an electron because each atom has an additional proton. So we can follow along on the boxes and use the orbital blocks to fill these diagrams. Okay, let's do another one as well. This is example 2. Let's use the periodic table and write the electron configuration for iron. So we need to figure out first how many electrons iron has. It's down here, this is our target, and it's going to have 26 electrons. It's atomic number 26, so when we have a neutral atom of iron, it's going to have 26 electrons. Think about for a second here, if you had a iron ion, a cation of iron, say like iron 2+. Iron 2+ has 2 fewer electrons, so if you're writing the electron configuration for iron 2+, you'd be writing it for 24 electrons because it has 2 less electrons than neutral iron. So you'd fill up till you got to 24 electrons. And there's a couple challenge questions at the end of the homework that ask you to look at some ions and fill their electron orbital diagrams. But let's do neutral iron and fill it up. So again, you always start up here with the lowest energy orbital, which is the hydrogen subshell, the 1s subshell. So we're going to start with 1s, That obviously has to be filled. We got to get all the way to 26. Then we go down to 2s. That's got to be filled. Then we jump across to 2p. The p block holds 6 electrons, so neon's final electron would be in the 2p6 designation. Then we jump down, keep Xing out these boxes. Now we jump down, we're in the 3s block. We've got to fill that. 1, 2, skip across to 3p. We've got to fill that. Then we're down in the 4s. We've got to fill that. I'm just going to move these down so we've got a little bit more space. And now we're in the D block. We've got to get all the way here to iron. And remember, when you're in the D block, you have to subtract 1 from the row number. So we're in row 4. That's why we filled 4s. But with the D block, you have to subtract 1 from the row number. So this is the 3D block. It says right there 3D. And we're trying to get to iron right here. So we need to add 1, 2, 3, 4, 5, 6. 6 electrons to the 3D block. 1, 2, 3, 4, 5, 6. And that's it. You've just written the electron configuration now for iron using the periodic table. Let's do another one. Let's do something all the way down in the F block. Uranium way down here. Okay, so again, you always start in the top left. Uranium is atomic number 92. So we're going to have 92 electrons we've got to keep track of. But as long as we follow the filling pattern, we're going to get all the way to uranium at 92. I'm not going to be able to fit it on one line, so we're going to have to kind of break it up. But let's start this. So you start 1s2. Done. Next, 2s2. 2p6. That's all of this. 3s2. That's there. Then we're into 3p, can hold 6. Then we're down to 4s, it holds 2. Now we're in the 3d, and the D subshell can hold 10. So let's fill this whole one up with 10. Go on to the next highest energy orbital, which is the 4p, can hold 6. Just so I can keep track of where I'm at, I'm going to start in the next line with 5s, it holds 2. Then we're in 4D, holds 10, fill that up. Then we're in 5P, P blocks can hold 6, fill that up. Now we're in 6S, can hold 2. Then we've got to jump down here to the lanthanides. So we're in the 4F block, and the F blocks hold 14. So we fill all of this. And now we're back to lanthanide right here. And so we do 5D10, fill that up. 6P6, fill that up. We're finally down here to 7S2, fill that. And now we jump down to the second row of the F block, starts with thorium. So we have 5F, 1, 2, 3, 5F3. And that's it. That's the whole electron configuration for uranium. And we could count up all of these electrons, 2 + 2 + 6 + 2 + 6, and it would add up to 92 electrons. So as you can see, this gets really tedious. Can you imagine drawing the boxes for these, the orbital diagram? It would be a whole bunch of boxes. Even writing it like this gets quite tedious. And so to help us with that, we use those shorthand or noble gas configurations. Before we do some examples with that, I just want to briefly talk about what are called valence electrons. The valence electrons are really special because they're the electrons in the highest energy shell and any unfilled subshells. These are really important. We're going to continue to talk about these throughout the class because since they're the highest energy electrons, they're in the farthest out shells. They have the most energy, and they're going to be the ones that are involved in chemical bonding and chemical reactions. What's really, really cool about the way the periodic table is set up, remember those groups, the columns are arranged so that elements with similar properties are in similar columns. Well, using the blocks on the periodic table, elements that have similar highest energy electrons, similar valence electrons, are also arranged that they're in the same groups on the periodic table. So to show what that looks like, we're going to write the shorthand, the noble gas electron configuration for these 4 elements, and then compare what their highest energy electrons look like. And we'll see, because magnesium, calcium, strontium, and barium are all in the same column of the periodic table. They're all going to have similar highest energy, right? Which means highest N electrons. And those highest energy electrons, those are the valence electrons. So let's start with magnesium. Let's write the shorthand electron configuration for magnesium. This will give us some practice with shorthand configurations. So for the shorthand configuration, you look for the previous noble gas. So if we go backwards on the periodic table, the previous noble gas is neon. So we can say magnesium has all the electrons of neon plus these 2 electrons in the S block. So plus 3s2 electrons. We then look at calcium. Let's do calcium in a different color. The previous noble gas for calcium, because we're doing shorthand method, is argon. So we're going to write argon. And what we're saying is that calcium has all the same electrons up to argon. And then we're going to write whatever additional ones it has after that noble gas. So it has everything that argon has. And then it's in the 4s block. So 4s, and it's 2 boxes in. So 4s2. Let's check out the next one. Strontium. It's down here, Sr. If we write the noble gas configuration, look for the previous noble gas, so that's krypton. So it has all the electrons that krypton has, plus it has 1, 2 electrons in the 5s orbital, 5s2. And last but not least, let's check barium. Barium's right here. So the previous noble gas is xenon. So the shorthand configuration for barium would be Xe. And then it's in the 6s block. So 6s. And you count over 2 boxes, 6s2. So if we check out the highest principal quantum number and the electrons in there, for each of these, they all have the same type of orbital with the same number of electrons, right? Their highest orbital is all s orbitals with 2 electrons. So these are the valence. So all of the elements in the second column of the periodic table have 2 valence electrons, and they're located in an s orbital. S orbital, 2 valence. The s orbitals are getting bigger as you go down the periodic table, but those kind of types of orbitals that they're located in and the number of electrons in the farthest out orbital is similar. And that's why these elements in the second column of the periodic table have similar properties. So the whole periodic table is arranged like this. So any element looking down a column is going to have similar highest energy electrons, valence electrons. Let's check out another example. Let's look at a few elements here: oxygen, sulfur, and selenium. So if we write out the configuration for oxygen, And let's do full configurations here, just to really get some extra practice. So we're going to do oxygen first. So 1s2, 2s2, 2p. So we're here, 1, 2, 3, 4, 2p4. We next do sulfur just below oxygen in the periodic table, right here. 1s2, 2s2, 2p4. So we 2p6. 2p6. So we filled here. Here we got down to 3s2. And then 3p, 1, 2, 3, 4. 3p4. If we do the same thing for selenium, going one more down. Right here. 1s2, 2s2, 2p6, 3s2, 3p6, and now we're down here. 4s2, 3d10, filled up all the way to here, filled up all of these, and now we're in the 4p, and it's going to be 4p4. So now if we look at these configurations for these 3 elements that are in the same column of the periodic table, we look at these 3. If we look at their highest energy electrons, those are going to be in the electrons that have the highest principal quantum number. Highest energy electrons have highest N. So we look for the highest N. And here for oxygen, we have 2 is the highest N. So that means it has 6 valence. We count up all the electrons in the highest N value. 2 is the highest for oxygen. We don't count those ones in the 1s orbital. So 2 plus 4 equals 6. We check sulfur now. 3, the N value of 3 is the highest. So we're going to count up these ones. 2 plus 4 equals 6 valence electrons again. And if we check for selenium, we just look for the highest N value. So 4 is the highest. So we have 4s2 and 4p4. So they still add up to 6. This 3D, right? It's a principal quantum number of 3. So it doesn't count as the highest. You just count the ones in the highest principal quantum number orbitals. So 6 valence electrons. So all of the atoms going down this column are going to have 6 valence electrons. They're going to be located in the s and the p orbitals moving down the periodic table. So because their highest energy electrons are similar, they have the same number, they're in the same types of orbitals, these elements all react similarly. Okay, so our next section is going to be on the explanatory power of the quantum mechanical model. Kind of what we've just been talking about, how quantum mechanics fits in with the periodic law and how they work together to help us better understand how atoms behave. I'll see you then. Thanks, everybody.